Hello and welcome to this NIER paper presentation with the title, Did You Do Your Homework? Raising Awareness on Software Fairness and Discrimination by Sarro and Max Hort, which is me, both from University College London and the Solar Research Group. As this title indicates, in the next few minutes we will look a bit into software fairness, why it is important, how it can be measured, and some fallacies that you could encounter when trying to mitigate bias and to improve the fairness of software systems. So let's at first look into why this is actually an important topic to look at. You might have already seen some headlines similar like the two shown on this slide, which indicate there is bias in software systems that oftentimes rely on machine learning and, for example, risk assessment and also facial recognition software. So as a beginning point, let's define fairness, and we specify that fairness is the treatment of individuals based on merit rather than sensitive attributes such as gender or race. Such attributes can also be called protected attributes. Because what can happen if you don't take this into account is that you use software and the software has a different behavior towards different population groups. So you end up with a privileged group which receive a systematic favorable treatment and an unprivileged group which receives a systematic unfavorable treatment, and that's something that you don't want to do, in particular if the groups are divided by sensitive attributes. Let's next look into how to measure fairness, or also the degree of bias a software system holds. The smiling faces represent favorable treatment and the frowning faces unfavorable treatment. And as you can see, 6 out of 8 individuals in the privileged group receive a favorable treatment, therefore 75%. And in the unprivileged group, it's 3 out of 6, which ends up being 50%. The disparity of the favorable treatment is therefore 25%, which indicates that there is bias. An unbiased system would have a disparity of 0%, so this metric should be minimized. Taking this into account, we will now look into some scenarios to ask ourselves when is treatment of individuals fair, and is it fair all the time to only consider such metrics? The example shown is a very simplified grading system for students. We have 2 students that differ in appearance, which is the sensitive attribute. They do homework or don't do homework, and they receive a grade. And what we want to do is we want to give students a fair grade without taking into account the geometric shape of their appearance. In the first example, you can clearly see that the 2 individual students share the same grade, and they only differ in appearance. So we could say that this is fair. They have both the homework, same grade, so there's no disparate treatment for appearance. If we now look at the second scenario, it is not as clear-cut anymore. The appearance, or the groups based on appearance, are still treated equally. 100% of the students in both groups get an A. However, you could start asking yourself, is it fair to give someone who didn't do homework the same grade as someone who did do homework? Which is why in some metrics this would be still fair because the 2 groups are treated equally. However, if you divide the population into groups based on doing homework and not doing homework, then this would not be as fair anymore. So we are trying to consider not only protected attributes such as gender, race, or age, for which you want to minimize the bias or the discrimination, but also anti-protected attributes such as doing homework, for which you want to maximize the disparity. In the example we've seen, we might want to maximize the difference in grades for people who did homework. For example, they get an A, and for those who didn't do homework, so they might get a lower grade. We test this on a very popular dataset in fairness research, the adult dataset, which contains information about census data of 48,000 instances, and there's a label based on the income, whereas having an income above $50,000 a year is favorable and below is unfavorable. There are two protected attributes, gender and race, and we try to devise anti-protected attributes for which we want to maximize the disparity. However, here we need to state a warning that by no means do we want to say that you should treat groups based on working hours per week or education differently. However, for the sake of this example, we try to find features which are not as disruptive as if you imagine you have identical individuals that only differ in hours per week worked. It would be reasonable to have a different income. Same for education, as studies have shown that a higher level of education often can lead to a higher income. But as stated, this doesn't mean that you should do it. You should always take into account your application when trying to optimize for fairness. So we now try to optimize a logistic regression model using grid search. You can see the parameters listed here, which we use for tuning. There's more details in the paper. And to quickly show the results, we compare it to two existing bias mitigation methods, reweighing and equalized odds post-processing. Bold values show improvements in regards to the base model, and as you can see, existing methods are able to reduce bias for protected attributes, but they're not able to increase bias for anti-protected attributes. So we showed that it is possible. But in conclusion, I want to say that fairness is very complex, and if you want to improve fairness in real-world applications, you need to take into account a lot of different aspects. So for the future, we see that it is important for software venues to include fairness research, but also it could be interesting to devise more multi and many objective algorithms for improvement so that whoever's using them can manually tune them and choose the objectives.